Yo, what's up guys? Welcome to the second episode of the Recursive Arrays series. This episode is made by Voidy and may be published elsewhere by his friend Simon. There is some presentation error. Okay. Make sure to watch the first episode of this series or otherwise you may not understand this episode, okay? So, if you haven't watched episode 1, please watch it. The episodes are highly interconnected, so please watch it. Are you sure you want to proceed watching this video? If you are sure, then I want you. Please watch that. Today, we will solve for linear recursive arrays when P is 3 and C is 0, step by step, and conclude the formula for every P that is a positive integer and C is 0. To conclude the formula, we must cheat a bit, or we will calculate or the previous calculation compared to the calculation required will be very oblivious. So we need to conclude a broader formula from the previous formulas using the symmetry and elegance of math. Without any further ado, let's get right into it. So when P is 3 and C is 0, this recursive array is in this presentation. An plus 3 is B2 times An plus 2 plus B1 times An plus 1 plus B0 times An. Our assumption is to make a reasonable guess, or not a guess because this is almost guaranteed to happen. We want this thing to be identical to this thing where x, y, and p are constants that we may pick. So when these two equations are identical, we can use this technique called An elimination to eliminate one of the unknowns and to simplify the problem. You see, A2, A1, and A0 are constants. X and Y are also constants, but as the P to the n plus 1's power is only about n, so we just eliminated An. If we do it 2 more times, we can get the formula. So this idea is from my previous 2 videos, right? So I will not explain it this time. Make sure to watch my previous video. Let's directly solve for x and y. We just break it apart and to make the formula a bit more clear, we can conclude that An plus 3 is x plus p times An plus 2 plus y minus p times x times An plus 1 minus p times y times An. But we also have this equation. So this is identical to B2. This is identical to B1. And this is identical to B0. So we can get a set of equation x plus p is B2, y minus px is B1, and minus py is B0. We may solve for p, x, and y, but let's leave it for now. And we have this equation, we can deduce with it, and we get p squared times An plus 1 minus x times An minus y times An minus 1, and we do it, dot, we get p to the n plus 1's power times A2 minus x times A1 minus y times A0. So we can conclude that An plus 2 is x, An plus 1 plus y, An plus p to the n's power times this thing. Because we can happily replace n plus 1 with n here and move these two parts to the right. we can happily move this to here and replace n plus 1 with n, right? Now, try to pronounce this thing is very difficult, so we want to call it f. So, an plus 2 is x times an plus 1 plus y times an plus p to the nth power times f. And we eliminated an unknown. Now we make a second assumption. This is the same idea, just in another step. So our guess is an plus 2 minus q times an plus 1 minus un plus 1, which is something mysterious about n. Is identical to r times an plus 1 minus q times an minus un, because we can deduce using the same idea, right? So an plus 2 is q plus r times an plus 1 minus q times r times an plus un plus 1 minus r times un. And that is identical to x times an plus 1 plus y times an plus p to the nth power f. So let's just politely ignore this part and this part for now, and just know that they are identical. We want to try to do the equation for these two parts first. So q plus r is x, and q times r is negative 1. And we have another set of equation. X plus p is b2, y minus px is b1, and minus py is b0. What if we combine these two sets of equations? After we combine this set of equations, just replace x with q plus r and y with minus qr. Something magic happened. Things are symmetrical and organized. P plus q plus r is b2. The opposite number of p times q plus q times r plus r times p is b1. And p times q times r is b0. This expression is quite familiar to us. Why? Because it satisfies a very, very famous theorem. And these PQR are the solutions of the trinomial equation t cubed is equivalent to b2 times t squared plus b1 times t plus b0. Now let's politely take a look at our ignored part. Un plus 1 minus run is f times p to the nth power. As f is a constant, we guess that un is a constant k times p to the nth power. So k times p to the n plus 1's power minus r times k times p to the nth power is f times p to the nth power. We can just remove the p to the nth power here on both sides. So k times p minus r is f. So k is f over p minus r. Now we can always calculate f using q and r over here, and we can apply the f to k to get this expression, and we have un is k times pn, p to the nth power. Hail an elimination. So with the formula deduced, we can just apply the steps over and over again, and we can get the thing that an plus 2 minus q an plus 1 minus un plus 1 is r to the n plus 1's power times a1 minus q times a0 minus k. We politely replace n plus 1 with n, and we get the formula an plus 1 minus q times an minus un is r to the n's power times a constant, which is a1 minus q a0 minus k, and we'll call it g here. So an plus 1 minus qan is k times p to the n's power plus g times r to the n's power. We find somewhat symmetrical things here, because I don't know the noun for symmetric. So, according to our previous experience, we want these two things to be identical. An plus 1 minus v times p to the n plus 1's power minus w times r to the n plus 1's power equals q times an minus v times p to the n's power minus w times r to the n's power. And that is a reasonable guess. What to do now is very easy, right? An plus 1 is just qan minus this, because we can easily do the computation, do the algebra, and it is also identical to this. So v times q minus p is k, w times q minus r is g. So we know that v is k over q minus p, w is g over q minus r. And this is one final step. We apply the given formula again and again and again until we do it n plus 1 times. We get an plus 1 minus v times pn plus 1 minus w times rn plus 1 is q to the n plus 1's power times a0 minus v minus w. This is also a constant, right? So we now let this to be t. And we replace n plus 1 with n. So this is the formula. An is v times p to the n's power plus t times q to the n's power plus w times r to the n's power. And v, t, w are constants, and you can easily calculate them. Since v plus t plus w is a0, we may suspect that vp plus tq plus wr is a1, and vp squared plus tq squared plus wr squared is a2, because we can just always apply 1 and 2, plug it into this formula and get the equation. We suspect that, and if you examine it, it should be true, either with the Cramer's rule on v, w, and t, or by brutal computation. You can always prove that this two things is true, but if I prove it right now, the video will be about an hour long. So if you check the result of the trinomial one we've just done and the quadratic one we've done in the last video, because we assume you've watched the last video, you may suspect that for n plus p is the sum of I equals 0 to p minus 1, bi times an plus I, and a0 to ap minus 1 is given, and bi is given. We can always let r0, r1, and rp minus 1 be the roots of this equation. Just replace an plus 1 with Just replace an plus I with t to the i's power, and we can get this equation. That is, this equation is this thing. This is a high-powered equation, and we can't guarantee a solution to it. But with a computer, you may get a not so accurate solution. It doesn't matter if the solutions are imaginary, it is a solution. And we want s0, s1, sp minus 1 be the root of a function is aj when j is 0 to p minus 1 integers, and we define this function as the sum of si times ri to the j's power added up from I equals 0 to p minus 1. Just see the p variable form of this set of equation. Then we can get the generating function for an. An is the sum of si times ri to the nth power sum up from I equals 0 to p minus 1. If you trust me, or you trust math, this is true. If you trust me or you trust math, this is true. If I prove it here, this video could be a century long, but we can prove that it works for n is 1, and if for m is k it works, and it should work for a is k plus 1. We can always prove it this way, but I will ignore the proof here. According to the elegant and symmetric math principles, this is true, right? So thanks for watching. If you are viewing this on YouTube, please leave a like and preferably subscribe for more contents and missed contents. If you aren't watching this on YouTube, please consider move to YouTube for direct contact for me and access to more content. Check out my spoiled fast noodles and my channel. Thanks for watching.